so thinking about this subject, so is philosophy useful for mathematics and or vice versa? I have to say that I was a bit unsure what to make of it for some time. So now, but so I was basically faced with the following puzzle, which is a very basic question, which also applies to the original question with science instead of mathematics. And this is, so I think that you basically have four different options when you look at this question. So one of them is, so is the question really about the interaction between philosophy and mathematics seen as two different disciplines? So something like chemistry and biology. So in that sense, they would overlap. And so in that sense, is the overlap useful for either discipline? Or then, is the question whether mathematics as a discipline can be the object of philosophical scrutiny, and whether the insights that could be gathered from this scrutiny could feed back into mathematical research. So that, of course, I think many people in the audience here might want to answer this question positively, but that's... And then thirdly, you can ask the reverse of this. So namely, could it's whether mathematical research can mathematical research lead to new philosophical insights? So I mean, and finally, the fourth option is, I mean, so puts things in a more general context. And then the question is whether a part of mathematical practice, or mathematical practice at large, but not mathematics itself, is actually driven by philosophical concerns. So in other words, I mean, is it true that philosophy comes into play when we try to define sort of the historically shifting boundaries of mathematical research, of what it actually means to do mathematical research? So in short, so is the question about the overlap between mathematics and philosophy, or is it about the application of philosophy to mathematics, or about the application of mathematics to philosophy, or is it about mathematical practice or culture as a natural turf for philosophical thinking? So, okay, so this talk will not be have very much of a slide structure, but let me just put this on a slide. So, because these are four basic questions I would like to consider now. Here we are. There, exactly. So here we have all four questions. Okay, so now I'm going to look at these questions each in turn. So, but before I actually look at these questions, which I think very much have something to do with some of the talks I've already heard, because I think some options are taken there in these talks with respect to these questions. So it is, of course, necessary to have a working definition of what mathematics and philosophy are as disciplines. I mean, at least, I mean, a loose definition. And, well, as is well known, this is actually quite difficult. So the problem of the definition of philosophy, that's, of course, a very old one. And it is actually, as such, a kind of philosophical problem. And in fact, it is often when, you know, an honest attempt to negate the very existence of philosophy is made that new philosophical insights are gathered. So, but in the context of this talk, my working definition of philosophy, so very loosely, it is that it is an attempt to understand the boundary conditions of knowledge, or in other words, what constraints our attempts to understand the world faces. And this is, I mean, certainly a problematic definition, and it's quite possible that it doesn't even make sense ultimately because it's to some extent self-referential, so it's logically problematic. But I mean, here again, I mean, this kind of thought process is typically a philosophical one. So the only concrete definition of philosophy one can give is probably historical rather than conceptual. But I mean, okay, I don't want to dwell on such matters very much in this talk. So here we go. So philosophy is about boundary conditions of knowledge. And now, if we look at mathematics, so that's another, of course, I mean, that's another hot potato. So it's a hotly debated topic. And it already, in fact, it's a very old, of course, philosophical concern, and it was a philosophical concern of the Greeks. So, for instance, famously Aristotle's Metaphysics, the 13th book is entirely about that question. And but what I propose here to do is again, sort of take a very sort of maybe more of a historical stance. So I propose to see mathematics in the light of its relationship to the experimental sciences. So scientific theories are always expressed in mathematical language. And once the theory is thus expressed, so it becomes independent of the experiment which gave birth to it, and can be made the object of an independent investigation. So this is a typical scientific process. It leads to a mathematical theory, but then the mathematical theories stand alone, and you can do logical deduction, mathematical deductions that will actually then have some consequences for the real world. And so any further results about a mathematical theory expressing a piece of scientific knowledge are then of an objective nature and will hold irrespective of any further experimentation. So in this sense, mathematics is the ultimate goal of scientific knowledge, because once a mathematical theory can be formulated, which is a model, something we've seen already in the conference, of a say, a physical situation, then the link with that physical reality is actually severed. Okay, so therefore I see mathematics as the ultimate goal of scientific knowledge, in the sense that you formulate something that then is actually independent of experiment. Now, with these provisional sort of definitions in mind, I now want to return to the questions 1, 2, 3, and 4 that you can still see on the screen here. So if you believe these definitions, so then both philosophy and mathematics have something to do with the very nature of knowledge. So in both disciplines, one is concerned with knowledge outside of purely experimental context. However, a basic difference between the two is that a mathematical insight can have real-world content. So for instance, if I look at the solution of the differential equation describing the movement of a ball that's thrown into the air, although it's obtained in the non-experimental context of mathematics, because you've solved a differential equation, it expresses something that can be tested in the real world. On the other hand, philosophy will not say anything about the real world, according to my definition. So, but would rather, for example, be concerned with the conditions that guarantee that a given statement says something about the real world, or about the type of knowledge that we can hope to acquire about it. So in that sense, the first interpretation here, is the question about the interaction between philosophy and mathematics. That seems problematic now, because it looks like philosophy and mathematics, although somehow fundamentally related, because they both have this non-experimental component, they do not operate at the same level, simply because mathematics can make experimentally verifiable statements, but philosophy cannot. So I would rather throw out the one. So that's my option here. So you might not agree with me, but then just bear with me. I will throw out many things here. So similarly, 2, that does not seem to be the right tack either to me. Because what happens there is that one superimposes philosophy on mathematics. And so if such a superposition, were possible, well, then mathematics would not be the final answer to scientific knowledge that it is. But it would have to be complemented by philosophy. So more concretely, if you believe in 2, if you think that answer 2 is positive, then that would suggest that conceptual thinking, say, about mathematical content, could help in the practice of mathematics and the solution of problems, and that this conceptual thinking is meta-mathematical, so is philosophical, if you want. But however, I don't believe that conceptual thinking about mathematical content is part of what I believe that it's actually part of what mathematics is, mathematical practice is, and it's therefore not of a philosophical nature. So for instance, I don't know, suppose you take a question like, are there any non-complete metrics on the field of real numbers? Well, I mean, I contend that this has nothing to do with this of course has nothing to do with real numbers, and is really a question about any set with the cardinality the size of the continuum. But to see this is not a philosophical insight, that's a mathematical one. So in that sense, I don't think that one can make sense of the idea of philosophical scrutiny of mathematics being helpful for mathematics. I mean, this is of course at odds with the point of view of some of the talks that I've already heard. But so that's my option for the time being. And also the other direction, so is it true that mathematics itself, so a mathematical result can have a philosophical consequence? I mean, I think that that's also problematic because, you see, if mathematics could feed into philosophical thinking, then we would be in the situation where the solution to a mathematical problem can have philosophical implications. But mathematics is technically, at least, it's a very self-contained and well-defined thing. So the solution of a problem in a, say, precisely defined logical context, like, say, arithmetics, so for instance, Peano arithmetics, cannot have implications for much wider questions about the boundaries of knowledge. I mean, of course, some people might say, okay, but maybe some mathematical results would and some others wouldn't. But I don't find that very satisfying because I think that either they all do or none do. I mean, So therefore, basically, I'm throwing out 1, 2, and 3. I mean, that is, I don't think that any of these have positive answers, really. So finally, I'm left with 4, which is, of course, where my money is, as you can guess now. So otherwise, I mean, this would be the end of the talk. So, and so I think, so that since both mathematics and philosophy try to say something about knowledge itself, so they must somehow interact in their cultural and historical development. And so this is what I will expand on. This is the point of view I will expand on in the rest of the talk. And I would like to stress, let me just, I would like to stress that I will focus on what I see as the interaction between philosophical thinking, I mean, philosophy as a thought process, and mathematics. So I will not focus on the various interpretations of what mathematics is that are given by various schools of philosophy. So, I mean, like, for instance, the Greek school, I mean, Aristotle, or then Plato, or German idealism, or, you know, or logicism, a la Frege Russell, or Brouwer intuitionism, or such things, you know, because these, that's outside of, say, of the conceptual range I want to look at, because in that case you give a static interpretation of what mathematics is a priori. I'm interested in a kind of historical, cultural interaction between philosophical and mathematical thinking. So I'm going to explain on a few examples what I have in mind here. So let me just stop sharing here. Yeah. So here's a basic example of what I have in mind, of where I think that philosophical thinking takes place. Although, in fact, as you will see, we are not talking about something that would have been done by, you know, some people called philosophers historically. So the fundamental example, the first example of this, the interaction between philosophy and mathematics, is, in my view, the introduction of the axiomatic method in geometry by the ancient Greeks. So because this method is nowadays so much part of our understanding of mathematics that one sometimes, sorry, I just need a bit more light here. Yeah, that sometimes one does not think that non-axiom-based mathematics even deserve the name of mathematics anymore. But however, I mean, as is well known, a large part of mathematics, both European and non-European, were developed with no axiomatic basis. So for instance, calculus, of course, was, I mean, this is well known, I mean, was invented and then studied intensively for over 2 centuries before it was given the proper axiomatic basis. And on the other hand, statements of calculus, I mean, even if they're given without the proper theoretical underpinning provided by an axiomatic system, I mean, they still play the role expected of a mathematical statement. I mean, in the sense that they are established outside an experimental framework and they can be used to make predictions about the real world. So an example here again is given by the differential equation for the movement of an object shot into the air. So this was solved early in the 17th century and has applications in, say, ballistics, even though the statement that the solution is a parabola was then not derived from first principles in an axiomatic system. It was basically computed in some modeled way, if you want. It's so, of course, the exact beginnings of the axiomatic methods of the axiomatic method are shrouded in mystery. But whatever its origin, it was introduced to explain what we mean when we assert that we have managed to establish a non-experimental mathematical fact. So that step that was taken in the 4th century BC to introduce axioms and proofs in mathematics, in practice we know this through Euclid, of course. I mean, that is not a mathematical step, because it does not amount to the introduction of a new mathematical object, and it is also not a deductive step. So it's not something mathematical, but it of course has a fundamental impact on mathematical practice. So I propose that such a step is a specifically philosophical step. Because if you believe in my description of philosophy as studying the boundary conditions of knowledge, then it certainly seems to fall under that heading. Because indeed, by introducing the axiomatic method, one tries to define what one means when one claims that mathematical knowledge has been gathered. So this method is put forward as a boundary condition for mathematical knowledge, for such knowledge. So anything asserted outside this framework will then not be considered established in mathematical context anymore. So this is the kind of cultural phenomenon that I'm interested in here. So I think that this is how, the interaction between philosophy and mathematics should be understood. So here, clearly, something of a philosophical nature has taken place, and on the other hand, it's clearly not of a mathematical nature. So now, if we look at the history of the axiomatic method, so as is well known, so this method has a long and distinguished history, and after the invention of calculus, it was for a time, put on pause, actually, and of course, in the Middle Ages, not much was done. But in the early 19th century, then, so I'm telling a very classical story here, but the abstract problem of the independence of the Euclidean parallel postulate from the other axioms of Euclidean geometry led to the work of Lobachevsky, Bolyai, and also Gauss, although it remained unpublished, and to the so-called non-Euclidean geometries. And then later to the proof by Klein and Beltrami that the parallel postulate cannot be deduced from the other axioms by giving hyperbolic models of non-Euclidean geometries. And so this is a major new step in the history of the axiomatic method, because the question of the independence of the axioms of a mathematical system had, to my knowledge at least, never been asked before that. Or asked or answered, although, I mean, maybe somewhere in Leibniz's work there are things about this that wouldn't be a big surprise if one. But so this is a big step, and then finally in the early 20th century, the axiomatic method ends up pervading all of mathematics via the axiomatization of set theory. And which proposes to provide an axiomatic basis for all of mathematics, and in particular for analysis, which had long been very reticent to be axiomatized. And then finally, later on, first-order logic is introduced, and axiomatic theory, I mean, the notion of an axiomatic, that is a theory, simply a set of, statements whose consequences you're interested in, together with independence problems and other questions about axioms, are then studied in an abstract setting, this abstract setting of first-order logic. So in that sense, that's the end of the journey for that method, which has now gone beyond just being merely used by the Greeks, and has led to the creation of a new mathematical framework, namely first-order logic. So, so I think that all through this historical journey here, something has happened at each step that is not of a mathematical nature, because for instance, the fact the widening of the field, the fact that you introduce first-order theories and that you look at first-order theories, this is an expansion of what, in fact, mathematical practice is about, but which is motivated by something which is not the solution of a mathematical problem. I mean, a mathematical problem that would have been there before. So this is a fundamental example of what I have in mind. And here, I want to give a second example. And I mean, I think there are a lot more, but I mean, I'm not going to go through all of them in so much detail. So here's another example. So this is a story that starts at the end of the 19th century, and I will just give a brief outline. And it's quite possible that if one digs, one will find that historically the story is certainly, I mean, it's certainly more complicated than the way I'm telling it. But so at the end of the 19th century, so there's a new approach to questions of commutative algebra emerged, which advocated the use of intrinsic as opposed to extrinsic methods. So the emblematic example for this is Hilbert's proof of what is now called Hilbert's basis theorem. So Hilbert's basis theorem, it's a very basic theorem of commutative algebra. As it happens, I'm lecturing. I've just today lectured on that theorem here in Oxford. So it says that so for instance, it has the following consequence, that a ring of polynomials in several variables over a field, so k, x1, xn, is Noetherian. So it means every ideal inside the ring of polynomials is finitely generated. For those who know what ideals are, but the ideals are just subgroups that are closed under multiplication by other polynomials. And so there's always a finite set of generators. And this fact, so the fact that rings and several of polynomials and several variables are Noetherian, this had been sort of conjectured, and I mean, many people thought that this was true. I mean, for a long time before Hilbert's proof. So Hilbert's proof was in 1890. So I think for about 2 decades before that, research was done, especially by the Germans, around this question. But now, the interesting thing is that, you see, the methods used by Hilbert, the methods used before Hilbert heavily depended on the fact that one actually looks at rings of polynomials. So those particular rings. And also, they insisted on being constructive in some sense, that is, implicitly. They worked only with polynomials, and then the idea was to, if you have an ideal, you want to create a set of generators. But on the other hand, Hilbert's proof used only the Noetherian property, and that is the fact that it only uses the fact that it. So how can I put this? So what Hilbert proof does is that it starts with any ring which has the Noetherian property, the one you're looking after, and then you simply show that a ring of polynomials over that ring is also Noetherian. And in that generality, if you have shown that, the solution to the original problem is easy, because you can then simply do induction on the variables. You see, you have then a field is Noetherian, then kx1 is Noetherian, and then, of course, kx1, x2, etc. All the other ones are Noetherian by simple induction. So in that sense, so it's a very basic structural insight, and yeah. So just and in fact, here's a funny anecdote about this, which is that so this is possibly an urban legend of some sort, but Paul Gordon, who was a German mathematician who worked around the same time, and he worked in a field called invariant theory that was very popular back then. But he had worked on that problem himself for decades, and he had also provided partial proofs for polynomial rings with small numbers of generators, small numbers of variables. And and he said, upon seeing Hilbert's proof, to find out that this is theology, it's not mathematics. And and indeed, I mean, there is a big shift in Hilbert's method, because what is remarkable about his method is that he insisted on using only a very special specific structural property, which is this Noetherian property, and in order to increase the generality of the problem posed. And then once you've increased this generality, the problem falls out. The problem becomes a lot easier to tackle. So in that sense, making the hypothesis weaker makes it easier to solve a specific problem. And this approach to sort of generalize the problem structurally in order to then approach a very specific problem where apparently using all the specifics of the problem will give you an advantage, this is a kind of something happened there in the history of algebra. And so in that sense, so you see, earlier approaches were happy to work in a very specific context, that is, in a polynomial ring over field, not over any Noetherian ring, and to avail themselves of some properties or facts that were only available in that context. So this had the advantage of providing more facts to work with, but it also hid the central structural properties relevant to the problem. So in that sense, Hilbert's approach can be described as intrinsic in the sense that it focuses on the structural properties relevant to a problem, whereas the earlier approaches can be termed extrinsic because although they were concerned with the same structural properties, they would not refrain from making use of facts only available in a very special case. Okay, so I think I'm going to, and okay, well, now after 1890, but of course, mathematics moved forward very quickly after that. But you see, in the 20th century, in the 30s already and earlier, you can see a general shift from extrinsic to intrinsic methods. So, for instance, you can see this in the new definition of a manifold. So, for instance, in Bourbaki's treatise on differentiable manifolds, which is now defined as a topological space with certain properties rather than a subset of some finite dimensional real vector space. That has to be, that is arbitrary, sort of. And you can also see it in the new definition of algebraic varieties, given by the Grothendieck school, so after the war. So in scheme language, what's called scheme language, where now the ambient projective space, was of course ubiquitous in the old approach, it does not play a role anymore. You have such a thing as an abstract variety. And also, finally, the intrinsic methods are at play in the development of commutative algebra. So especially in the work of Emmy Noether, where in fact Noether shifts the focus from quotients of polynomial rings by ideals with given generators to simply general, Noetherian commutative rings. So she has this classic paper called Idealtheorien Ringbereichen, I think, where she considers precisely that situation. So not polynomial rings anymore, which had always been considered, but a general Noetherian ring, which in fact, interestingly, Hilbert did not do in his original paper. So although he is the one who introduced this method, he did not actually go as far as actually defining a Noetherian ring, as far as I know. So this new distinction, so between intrinsic and extrinsic methods and concepts, so again, changed mathematical practice, although it is not in itself a mathematical step. So one could, of course, argue that Hilbert's proof of the basis theorem is simply a solution to an old problem based on a new insight, because after all, technically you can see it that way. But in this sense, it simply amounts to an understanding of what is needed for the proof. But however, you see, the thing is, in general, intrinsic methods are not always more efficient than extrinsic ones. So in the sense that the idea with the introduction of intrinsic methods is not necessarily that it's a recipe, that it's kind of miracle method. Sometimes it works less well. So for instance, I know that, if you look at differential equations on manifolds, so for instance, in the situation of general relativity, I remember from my student days, not my field, but that they're very often best handled locally in a coordinate chart rather than through the language of connections and curvature, the sort of the global intrinsic language, which in fact sometimes even seems to obscure what's going on. So it's not so that intrinsic methods are necessarily more efficient. The important point is that it has now, in fact, nowadays already, become standard to ask oneself whether a given notion depends on the specifics of a mathematical situation. And I think that this was not so at the end of the 19th century. So for instance, the first reflex of a modern mathematician, when faced with, say, the definition of non-singularity of a complex variety in terms of Jacobian matrices in a coordinate chart, so something where you need a coordinate chart to define the non-singularity, so you look at Jacobian matrices, then, is to ask whether there is a definition of non-singularity which does not, in its very formulation, depend on the choice of a chart. So you want an intrinsic definition, and this is something that one would immediately think, when faced with any kind of non-intrinsic definition, then you'd like an intrinsic one. And so in this sense, the distinction between intrinsic and extrinsic, it modifies mathematical practice, although the terms intrinsic and extrinsic are not really mathematical terms. So the introduction of this distinction, again, should be understood as a philosophical development. So it is certainly philosophical, according to that loose definition I gave above, because behind it is the idea that this dichotomy sort of draws something like a fault line across our mathematical knowledge, so that we can't ignore. You see, there's the question of whether things are formulated extrinsically or intrinsically. And this will be, ubiquitous in our mathematical thinking. So, yes. So yeah, and also, you remember that for the axiomatic method, I described these three stages. So there was the invention, in the context of Euclidean geometry, and then non-Euclidean geometries, and finally first-order logic in axiomatic systems. So something similar happens here for this distinction between the extrinsic and the intrinsic. So this strive for the intrinsic, this also led to a new mathematical framework, which attempts to catch the essence of this notion. And I think that this is category theory. So the one considered by, for instance, Evan Patterson in his talk. So in the sense that a category is a universe of objects in which one chooses to work, and one then asks what general properties of the category suffice to guarantee that these objects have certain properties. And once you have chosen to work in a certain category, it is only possible to use its general properties, and extrinsic methods simply cannot be applied anymore. In the sense that in a category, it is very hard to look at a given object. You can do that if you insist on describing the category with classes or sets or something, but it's very artificial. So, so in particular, in the language of categories, I mean, yeah, one can only talk about properties characterizing certain classes of objects, those so-called universal properties. And in this sense, category theory cancels the very individuality of an object, and therefore everything that could lend itself to an extrinsic reasoning. So it sort of forces you to be intrinsic somehow. And so, for instance, this categorical approach is, of course, at work in many structures of mathematics that are, that any undergraduate nowadays will see. So, for instance, at work in the modern approach to linear algebra. So, interestingly, yeah. So in the modern approach to linear algebra, so one looks at a category with certain properties that encapsulate the properties of finite dimensional vector spaces and linear maps between them. And then when making a reasoning, one never looks at a specific vector space. And this, of course, should be contrasted with, say, typically the older approach, where linear algebra is about matrices. And in that case, of course, when you look at matrices, you basically choose to identify a finite dimensional vector space over a field with kn for some n, but that's an arbitrary choice. So that's typically the extrinsic approach to things. So in that sense, in the history of linear algebra, the shift is very visible. Okay, so where am I now in my talk here? So I have given you, I've described two situations where I think that something philosophical happens, at the level of mathematical practice, and so I've given you these two examples, and then in these three examples, as we've seen, there's sort of kind of three historical stages. So I would like to make some comments on this. On the nature of this interaction between philosophy and mathematics, and basing myself on these two examples. But before I do that, I just would like to point out that I think that there are many other examples of such interactions. So, for instance, one could look at the development of set theory as a basic language for mathematics, and another example, which is of course very much linked to that one, is of course Cantor's study of the infinite. So, for instance, in that context, if I think of the previous talk by Hugh Wooden, you see all this hesitation about which set theory to choose. I mean, as Hugh Wooden said at the end of his talk himself, you see, this is really a philosophical concern. That is, which set theory, which axioms are you going to choose? This kind of, deciding what you're going to do, that is not something mathematical. So, yeah, and in fact, again here, see, Hugh Wooden talked about Turing machines. I think that the development of the concept of algorithm and the notion of Turing machine, that's another example of a development of that kind. And of course, one could also, for instance, another example that came to my mind is one could review the various attempts that were made in the early 20th century to understand the notions of identity and equality. I mean, the problem of what equality is, and is that is, of course, yeah, well, this has a long and distinguished history. Yeah. But now, going back to the axiomatic method, so one can see that there are three stages in the historical development of this method in mathematics. So in the first one, it is introduced in the case of Euclidean geometry, as I said. And in that situation, no questions are asked about the method itself. It's simply used. And in the second stage, the non-Euclidean geometry, you ask an abstract question about the axiomatic system of Euclidean geometry, which is the independence of the parallel postulate. And so this is the first sign of an attempt to understand this method in greater generality. And finally, a new mathematical framework to describe axiomatic system is created, and this is first-order logic. So let me just also recap what happens with this dichotomy between intrinsic and extrinsic. And this is, so here, the dichotomy, say, first appears in Hilbert's work on commutative algebra, but I'm sure one can give other examples, where he consciously insists on building a proof relying on basic structural properties. And then in the first part of the 20th century, and in particular in the work of the Bourbaki group, it then becomes standard to require minimal structural definitions of a new mathematical object. And finally, in the wake of, the work of Island, Burke, and MacLean, and under the impulse of Grothendieck later on, category theory is created and then developed. And as we saw, so this is a mathematical framework in which intrinsic properties can be studied kind of in vivo. So all this, you see this three-stage process for in both cases, that suggests that a certain epistemological process is at work when philosophical notions take hold in mathematical practice and then develop. And what I would now like to propose is that this process can be best understood in terms of an epistemological framework that was proposed by the Neo-Kantian philosopher Ernst Cassirer. I will quickly recall some basic constituents of part of what, say, Cassirer says in one of his books, and then I will make some comments on its applicability in this context. So I will now just talk for a little about what Cassirer calls symbolic forms, because I think that symbolic forms are at work here. So the symbolic forms were introduced by Cassirer in his three-tome book, The Philosophy of Symbolic Forms, that was published in the 20s and the 30s of the 20th century, and so he proposed in his book that human knowledge, say, has a certain structure which becomes apparent in history, when one looks at its unfolding in history. And according to him, so human knowledge in its historical development, sort of unfolding, has three phases. And so these phases, there is an expressive phase, what he calls Ausdrucksfunktion, and then there's a representative phase, what he calls Darstellungsfunktion, and then finally a semantic phase, the Bedeutungsfunktion. And when these three phases are completed, then one reaches a kind of a symbolic knowledge, where the three phases are one, but are still sort of in interaction with each other. And and then a historical instance of symbolic knowledge is then called a symbolic form. So now I have to explain what these words mean for Cassirer. So to explain what this means, the best, in fact, is to simply look first at an example, as a foundation example, which sort of should make it clearer. And for Cassirer, the foundational example of a symbolic form is language itself, so a human language. And so the expressive phase of language, it's the onomatopoeic component. That is the fact that many words actually reproduce the sound of what they refer to. So that is the most basic one. So this is a phase where language actually is somehow related to the very reality it tries to refer to. And now the representative phase, it's the purely representative function of language. That is the fact that many words refer to something simply by convention. So there's a convention that simply links words with objects. And so these words might still have an onomatopoeic origin, but it has in practice been lost, as indeed we do not know the onomatopoeic origin of many words. And now finally, the semantic function of language, so that is its grammatical and logical structure. So the fact that words can be organized in sentences and according to certain rules. So a fully developed human language, so a historical language, is then a prime example of what Cassirer would view as a symbolic form. So if you look at this example, so you can extract the meaning from there, So the expressive phase is a phase of knowledge where somehow a residue of the reality that is represented is still present. And the representative phase is one where a basic correspondence with reality is present, but on the other hand, knowledge is already somewhat removed from reality. And in the semantic phase, I mean, this basically you reach a kind of structural autonomy, a kind of dialectical logical autonomy, like in grammar. And on the other hand, the unity of the three phases, which Cassirer very much insists upon, that's very apparent in language. So indeed, when we use language, all these three phases are somehow present at once. Because well, what I'm doing now is I use all three at once. So somehow it's and so Cassirer calls full knowledge symbolic, because for him a symbol is basically a carrier of all these three phases in itself. So for instance, a word in language is a prototypical symbol, because it relates to the outside world through its onomatopoeic origin, but also through through the fact that its use in a social group is a convention. And then finally, because it can be used within a complex grammatical structure. So it's a kind of prototypical symbol. Okay, but now, in my view, sort of Cassirer's philosophy of symbolic forms should not be considered, in my view, as really a systematic epistemology. So the interest of this philosophy is that it provides a lens through which one can look at a large range of cultural developments. And in fact, in a large part of his book, Cassirer sieves through historical and ethnological data to find examples of symbolic knowledge in various geographical and social contexts. So there's an anthropological aspect to this. So let me just here share my screen again, just to remind you of these three phases, which I'm going to refer to a little later. So here, these are the three phases of symbol. So exactly. So just to recap now, the expressive phase, the residue of the reality that is apprehended is still present in our language, in our symbolism, if you want. And in the representative phase, there's a correspondence between the symbolism and reality, but the apprehended reality is not present as such in the symbolism anymore. And then in the semantic phase, the symbolism sort of goes wild. That is, it becomes independent and acquires a kind of internal, logical, and dialectical structure. Yeah. So now, so maybe I should. Yeah. So we have so try to remember these three terms if you are still with me. So yeah, so as it happens, mathematics itself is a very rich repository of symbolic forms. So that's something one can discuss at length. But that's not what I want to do here. So what I would like to suggest is that actually the interaction between philosophy and mathematics historically, according to the pattern that I've sort of described, it actually follows this pattern mapped by Cassirer's philosophy. So I think that it looks like throughout its history, mathematics has become the object of a certain kind of philosophical thinking, the philosophical knowledge, which unfolds according to as a symbolic form. So, for instance, let me just go back to. I hope I'll be able to convince you of this. So let's go back to the axiomatic method. So I think it's a prime example of this phenomenon, because in their original incarnation, the axioms in Euclidean geometry were understood to be self-evident statements, not statements arbitrarily chosen to be the starting point of the theory, like we would now. So this self-evidence has its roots in the fact that Euclidean geometry was supposed to be modeled part of the physical world. And the axioms reflected basic aspects of our experience of the spatial world. So in that sense, this first part of the story of the axiomatic method is, I see this as the expressive phase. That is, here we look at axioms, but what we actually look at is still very much sort of embedded in, see, the language we used is still embedded in the very reality that we're trying to describe. So that is, the axioms are not, they are still, they have their feet in, a certain physical reality they're trying to describe, because they're described as self-evident statements, not simply arbitrary ones. But on the other hand, in the development of Lobachevskian geometry, then one clearly moves away from physical geometry, and the axioms are not immediately grounded in experience anymore. However, in non-Euclidean geometry, the axioms of Euclidean geometry outside of the parallel postulate are still retained. So there's still a bridge to physical geometry. So we still have there this bridge. So this is the representative phase. And finally, when in the study of first-order theories, which is the object of mathematical logic, not even the historical link to Euclidean geometry that still existed in the work of Lobachevsky and Bolyai persists. And so this is clearly the semantic phase, where the notion of axiomatic system has acquired a kind of dialectical independence, because so we see that in that sense, the philosophical understanding of the notion of axiomatic system in mathematics historically sort of develops according to this pattern of cassura. And I would say the same thing for the extrinsic intrinsic dichotomy. So because when you look in Hilbert's original 1890 paper über die Theorie der algebraischen Formen, here I have the title. So there, in fact, he only looks at polynomial rings over fields, although the method can be generalized without much effort to general notarian rings. So in this sense, Hilbert's understanding of what intrinsic means is still rooted in the very rings that led him to think in this novel way. On the other hand, in her classic paper, Idealtheorie in Ringbereichen, Emmy Noether defines the notion of a notarian ring in full generality, and so there the link with the original motivating polynomial ring is lost. But however, you still have a bridge to polynomial rings because polynomial rings are notarian. So, and then finally, when you look at category theory, the notion of intrinsic property has acquired this kind of semantic independence that is characteristic of this last stage of the symbolic form. Okay. So so this is how I understand what I would I understand the interaction between philosophy and mathematics. So I hope that I've made a convincing point. So in that sense, that mathematics is a natural ground for philosophical thinking, and that this philosophical thinking unfolds in ways that are similar to other epistemological contexts, like indeed, in fact, inside mathematics itself, sort of funnily. And so in that sense, so what this means is that in our mathematical practice, we are under the dual pressure of mathematical problem solving on the one hand, and on the other hand, we are under the pressure of the paradigmatic shifting that is sort of affected on mathematics by philosophical thinking. So we have basically this dual pressure of philosophical thinking and purely mathematical thinking. And but however, I mean, as I argued above, since I gave these negative answers, to 1, 2, 3, 4, 1, 2, 3, in my list of 4 points, both aspects of mathematical culture, so the philosophical one and the really purely mathematical one, they correspond to different concerns. And so in this sense, they don't support each other. So in other words, solving problem in mathematics does not answer philosophical questions, and a paradigmatic shift in mathematics, which and doubtless they take place, but they do not contain as such a solution to a mathematical problem either. So if I now go back to the original question, is philosophy useful for mathematics and or vice versa? So my answer is that philosophy is very important for mathematics, because without it, somehow the mathematical field would somehow not expand. On the other hand, mathematics is useful philosophy because mathematical culture is such a fertile ground for the development of these philosophical ideas, the way I see it. And okay, so that's yeah. So that is my basically my conclusion on the interaction between the two. But you could now ask also the following, question, which is I think deserved somehow, which is that one could say that, well, is philosophical thinking around mathematics only a kind of intellectual luxury from the point of view of mathematical practice? Or is it really essential for the development of the mathematical sciences? After all, the way I described it here, I basically explained that philosophy was really useless for mathematics, but somehow that it expanded its field. But yeah, but on the other hand, so as I pointed out above, so the field of mathematical research would be less wide without specific philosophical thinking. But on the other hand, one could argue that the bulk of mathematics has not been much affected by this expansion. So, for instance, problems of applied mathematics do not require categories or first-order logic, or set theory, or the analytical framework of the 18th century would probably suffice for most applied problems. But on the other hand, one could argue that the thrust of a problem of applied mathematics, so that is in the sense where the problem to solve, where you do not actually practice mathematics internally, but try to specifically solve problems that directly come from, say, physics or chemistry, etc. So you could argue that the thrust in the problem of applied mathematics is not really mathematical. So the aim here is to solve a problem which comes from outside the mathematical field. So in that sense, an applied mathematician is rather a chemist, a physicist, a biologist, depending on what problems he solves. So there's absolutely nothing wrong with that, of course. And in fact, as I said above, it is in the context of real-world problems that mathematics was born in the first place. But however, when considering an applied problem, one is not engaged in a purely mathematical pursuit. So in this sense, the insensitivity of applied mathematics to philosophical developments is not really relevant. But that's okay. This is just maybe one objection averted. But there are other parts of mathematics which are definitely not motivated by real-world problems, where philosophical thinking does not seem to play much of a role either. So, for instance, one example of such a field is analytic number theory. So here, again, basically, the framework of analysis of early 19th century analysis is basically sufficient. And also from its very beginnings, unlike, for instance, for commutative algebra or algebraic geometry, the dialectical range of analytic number theory has not really expanded. So, in the sense that the concerns of Dirichlet, in the early 19th century, are very much the same as those of Hardy and Littlewood a century later. Even if, of course, technically, there's a big shift because, for instance, the Riemann hypothesis has become very important. So it's only the set of techniques which has expanded, and I think that from what I can gather from some discussions with other mathematicians, you could probably say the same thing of graph theory and combinatorics, for instance. But of course, my knowledge is limited here. And so therefore, you could then now ask, okay, so you have these fields which indeed have not been very much affected by any of these, philosophical developments. So is it so that in some parts of mathematics, in practice, very often the parts with algebraic rather than analytic concerns, the general take on what mathematical practice is differs from the other parts, in the sense that philosophy enters the picture, whereas it doesn't in other parts. And is this dichotomy between, say, non-philosophical mathematical fields and philosophical ones, say, is this a kind of accident? So, I don't really know how to make sense of that. But on the other hand, I think that this dichotomy, it reflects a very basic polarity in mathematical practice. And so in the context of this question, I just would like to quote, to show you an extract from a text by the Cambridge mathematician Timothy Gowers. It's quite famous. And this is a very interesting text called The Two Cultures of Mathematics. And this is, in fact, a kind of pun because it's a play on there's another text, by C.P. Snow written in this late 50s, also called The Two Cultures. So here he talks about mathematics. And so let me just share this with you here. Yes. So this is the extract. So this is actually a talk or a text, anyway, that it's on Timothy Gower's homepage. I found it's a very interesting discussion. And so here it is. So the two cultures I wish to discuss will be familiar to all professional mathematicians. So loosely speaking, I mean the distinction between mathematicians who regard their central aim as being to solve problems and those who are more concerned with building and understanding theories. And there I skipped something which is not very important. And as with most categorizations, it involves a certain oversimplification, but not so much as to make it useless. So if you're unsure to which class you belong, then consider the following two statements. The point of solving problems is to understand mathematics better. Or secondly, the point of understanding mathematics is to become better able to solve problems. And so this is an interesting distinction. So as a mathematician, you have to decide which statement you subscribe to. So most mathematicians would say that there's a truth in both 1 and 2, but not all problems are equally interesting. And one way of distinguishing the most interesting ones is to demonstrate that they improve our understanding of mathematics as a whole. But equally, if somebody spends many years struggling to understand a difficult area of mathematics, but does not actually do anything with this understanding, then why should anybody else care? So, however, many and perhaps most mathematicians will not agree equally strongly with the two statements. You see, I mean, that is, and indeed, I mean, if I think of the mathematicians that I know, I can imagine that they would answer these questions in a different way. So, okay, so you see, he introduces this very interesting distinction. So, is the point of solving problems to understand mathematics, or is the point of understanding mathematics to solve problems? So, yeah, so I think that one can go back to this extract in the light of what I explained before, because, so in the context of this extract, I would like to suggest that a philosophical development in mathematics is very much related to this question of understanding mathematics. But there's in the sense that I would argue that a philosophical development clarifies in some way what it is that we mean when we say we understand a part of mathematics, or at least it has something to do with this understanding, with what this means. So from this perspective, a part of mathematics where little philosophical development has taken place is likely to be more fuzzy as far as its general aims are, although, and I insist on this, these aims, if at all formulated, would not be specifically philosophical. You see, there's a kind of something paradoxical going on. So it is striking that in some areas of mathematics, like combinatorics or, say, analytic number theory, as explained, some problems seem to be put forward in a rather random fashion. So, for instance, it is often difficult to understand what motivates the many elementary problems of combinatorics that were put forward by Erdős, mentioned in the last talk, in his long career. You see, I mean, he came up with this whole sort of jungle, this zoo of elementary problems that don't seem to have much conceptual unity. And similarly, in analytic number theory, many results seem to coexist, again, I mean, with little conceptual unity. And at the other extreme, you could consider, say, algebraic geometry, which is completely dominated by the question of the existence of enough algebraic cycles and, the existence of a conjectural existence of a reasonable category of motifs, what's called motives. And so in that sense, algebraic geometry is the extreme opposite, because everything is dominated by these basic questions about the existence of algebraic cycles. And the thing is, you see, even if this question, for instance, the existence of algebraic cycles, are not as such philosophical, I mean, algebraic geometry in its present form, as developed by Grothendieck, would not exist without the important philosophical developments that led to the categorical notions which lie at the foundation of the field, for instance, of cohomology theories and many other things. So in that sense, to summarize, I think that the mathematicians who would believe that the point of solving problems is to understand mathematics better, so this is the first point mentioned by Gowers, are likely to be involved in a part of mathematics which has undergone a philosophical kind of paradigmatic shift. And now, whereas those who would choose the second option, I mean, there it's less likely to have happened. And of course, I mean, whether 1 or 2 is the better choice, that is something where I'm not going to say anything about that. But on the other hand, that seems to be quite a fundamental dichotomy. Now, I still also had something to say about experimental sciences more generally, but I think that I'm sort of running out of time, and I think it's maybe best to just stop here and just leave it at mathematics only. So thank you very much for your attention. Actually, yeah.
We have time for 1 or 2 short questions. Yes?
Yeah.
Thank you. Very good talk. Quick question in terms of the intrinsic and extrinsic. There is in topology, there is the Jordan curve theorem, which actually the intrinsic and extrinsic. So there is a geometric or topological equivalent to that. You don't necessarily need to go into category theory. Could you comment on that?
So just one, I didn't quite understand. So you say the Jordan curve theorem?
Jordan curve theorem, right?
Yeah, so that necessitated the introduction of algebraic topology, basically, for its solution. So are you thinking of something like that? Oh.
Yeah, so I'm saying that you can go from the geometrical point of view or topological point of view without referring to the intrinsic and extrinsic in category theory.
Yes, yeah, but I mean, the thing is, basically, all I'm saying is that, I mean, this specific example of Hilbert said from then on, I mean, people start thinking in those terms. Now, on the other hand, that's something that's superimposed to mathematics itself. I mean, it's not, it means you're going to ask a question. So, for instance, if you look then at a proof of the Jordan curve theorem, you would then, for instance, insist on trying to understand what the absolutely bare bones of the proof is, for instance. You see, I mean, would it then also work on a sphere or something, or would it? In what situations would it work? What is the exact generality in which the proof works or something? And I think this way of thinking is not something that's. I mean, I am a little interested in the history of mathematics, and when you read some of the 19th century texts, you don't see this kind of thing at work. I mean, there's definitely something happening there.
Yeah. Thank you.
Some other questions? Okay. Well,
I want to say one thing, Damian.
Yeah.
Where do you hear Chapman in person? So you are already invited publicly. Tell us when you will be able to come. Okay.
Yes. No, of course. And thank you very much for having been patient with the Zoom talk. Yeah.